All right, good morning. All right, so final exam is next Wednesday, December 16, 10:30 to 12:30. We will be in Elliott Hall of Music on the main floor. And take a look at this map. It's also posted on the course webpage. Please make sure you know where to go. It's by TA as usual. But if you get there, you have no idea where to go, just either look for your TA or look for me, and we'll send you to the right place. Okay? All right, so if you responded to my survey, thank you. These are very useful. So today we're going to look at the Fall 2014 exam, and we're going to go in this order based on the popularity here. Let's start with number 6. Number 6, you have this conical tank with a height of 2 feet. And the radius at the top is half a foot. Full of water. Now we're given the water weight density. We like to find out how much work is required to pump all of the water to the top of the tank. Okay, so that's a setup here. You got a cone that's with the pointy end down. Two feet tall. So from the point to the flat top here, it's 2 feet. And the radius at the top is 1/2. And right now it's full of water. We want to pump this water out of this tank over the top. We want to find the amount of work required. The basic formula we need to know is that work is found by integrating the force times the distance. Force in our case would be gravity, the weight of the water due to gravity, and distance is how much it has to travel over the top to get out of the tank. Okay? So as usual, we consider a very thin slice of water right here. And by the way, let's make the bottom of the tank y equal to 0. And then the top of the tank, we'll make it y equal to 2. So first, let's consider the force component of the work for that slice. The force is the weight. Okay, the weight is the mass density, the weight density, times the volume. 62.5 times the volume. This is a disk, right? So it's pi radius squared. And then the thickness is dy. Now, the next thing we need to note is that the radius of the slice changes with height. It's a function of y, right? At the very, very tip here, it's 0. At the top, it's 1/2. So as it goes from the bottom to the top, it's going to change. So that's the next key part in this equation. To find out the dependence of radius on y, let's take a side view of this cone. It's a triangle, and then chop it in half. Like that. This is 2. This is 1/2, right? And now my tiny slice here, let's say is right here. Call the radius r. And call the height, the arbitrary height of that slice, we'll call that y. Okay? And now this is perfectly set up for using similar triangles to find r as a function of y, right? We know r over y is equal to 1/2 over 2. So therefore, r is equal to 1 over 4 times y. So that's going to take place of that radius quantity in the weight equation. Okay? Next, we'll find out the work for that one slice. The weight part is easy, 62.5 pi radius squared times dy, that's the weight. What about the distance? How much does this arbitrary slice I sketched have to go to reach the top? 2 minus y, very good. Distance to go, right? It already attained the height of y. It needs to make up the difference to go to 2. Okay, now we want the entire tank, right? So we integrate from 0 to 2, and then we'll get the whole thing. Remember, the way to do these things is you set up one slice and then integrate to get the entire shape. Focus on just that one slice and then do the integration. All right, so let's finish the integration. Let's take out the constants. I have 62.5, a pi, and a 1/4 squared. So let's do it this way. Right? The 16 came from 1 over 4 squared. And then inside here, I get y squared times 2 minus y. So 2y squared minus y cubed dy. And now the easy part, y cubed minus y to the 4th over 4, 0 and 2. So that's 8 minus 16, 4. So that's a 4. That's a 2. Yes, 2/3. Sorry. That's right. So this will be 16 over 3. My mistake. 16 over 3. And then inside here, this is 4 over 3. So 62.5 pi times 1 over 12, right? Okay? Questions on this? Good? Good. All right, survey says the next one is number 13. Which of the following sequences converge? Here's 1, 2, 3, 4, 5. Then the last one. All right? Okay, so remember we look at sequences and series and we talked about their convergence. So a sequence converges if what happens? Yeah. That's right. Exists, right? So whatever the number it is, it does exist. Okay, so let's look at these things here. The first one, what's the limit when n goes to infinity? Does it exist? I guess the limit doesn't matter. Does it exist? Yeah, so this one converges. Put a check mark there. How about this guy here? The 1 over n part, what happens to that when n goes to infinity? 0. Now what's this doing then? Just bouncing back and forth. So overall, is there a limit? No, there's no limit. This thing eventually becomes irrelevant. And then it's just bouncing +1, -1, +1, -1, kept on going. So this one does not converge. How about this one? No, right? It's pretty clear. Here? Right, because this one, remember, turns into that, right? Oops, there's no factorial there. So this is really just 1 over n plus 1. So this one is good. How about the last one? It does, yeah. Just remember, exponential always trumps a factorial function. You can try putting in a few numbers of n and find out what happens, but exponential trumps just about every function we encounter. So we're seeing what? Oh, wait a minute. No. It doesn't. Let me take that back, because this is actually putting 10,000 here. This is 10,000 times 9999 times 9998 10,000, 99999, 9998, and keeps going. All right? And then this is 2 times 2 times 2 times 2 times 2, 10,000 of these. And how many of these are upstairs? 10,000, right? Okay. So we just have to look at these things. This is 5,000. This is something like 5,000. That's something a little bit like 5,000, right? So this is a big, 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 big number. This is one way we can see that without the factorial, then this is obvious. Exponential trumps. But with factorial, things are a bit different. So this is a no. Therefore, 1 and 4 are good, and the rest are not. Questions? Yeah. The first one? The limit exists. When I let n go to infinity, plus 1 and minus 1 don't matter. So therefore, we have n over n, and that's a 1. Yep. And as long as we get the limit, regardless of the actual number, then the sequence will converge. That's not the same as a series, right? A series converges. The convergence of a series is a much more difficult question to analyze. Okay, good with 13. Next one, survey says number 21. Oh, this one is fun. This one is fun. We want to use the first 3 terms of the binomial series for this thing here to estimate cube root of 1.1. Okay? We will give you the binomial series, 1 plus x to the power of k So you will get that if this question like this were to show up on your exam. This will be printed right there. Okay, so the first thing we have to do is to get first 3 terms for this one here with that specific k, and then we worry about that. So here and I got the 3 terms here. We're going to truncate it right after that. 1 plus 1/3 x plus 1/3 negative 2/3. 2 factorial is 2. And then 1/3 negative 2/3 negative 5/3. 3 factorial is 6. Oh, let's write it 3 times 2, because we might be able to take advantage of cancellation. Yeah. That's right. That's 4, right? 1, 2, 3. Oh, good. We don't have to worry about this one. Goodbye. 3 terms. Forgot that 1, you know. It looks so simple, I almost don't want to count it. But anyway, it's a term, 1, 2, 3. Good. Okay, so we got this thing here. So 1 plus x to the 1/3, three-term approximation will look just like that. If you want cube root of 1.1, this is 1 plus 0.1 to the 1/3, right? So you simply have to put in this 0.1 in the place of x here, and then simplify. So we get 1 plus 1 over 3 times 1 over 10. And then here, this is a negative overall here. Negative 1/2 from downstairs, 1/3 upstairs, 2/3 upstairs, and then 1 over 10 squared. So I think that's all we have to do here. Looks like E is the one. All right, they left the minus sign in here and write this as 100. Same thing, right? So this is good. Okay, so the key here is the binomial series. Again, we'll give that to you, so you will have that to work out things. Questions? Nope? Okay, good. Number 4. The next one is number 19. Oh, this one is another fun one. This is good stuff. Good stuff. We want to find the Maclaurin series of this thing. Okay, you need to know definition of Maclaurin series. The definition? No. Now this you have to know. Okay. However, this is not the way you want to do this problem, because you don't want to take derivative of this even once. Oh, I don't want to. Okay? So that's okay, but not a good way for this problem. We'll give you specific Maclaurin series, like, for example, sine of x, cosine of x, that kind of thing. But the general definition of Maclaurin, that's something you have to know. We'll give you specific ones. The only one we will not give you is the geometric series. So who remembers what the Maclaurin series for 1 over 1 minus x looks like? You have to know this one. I'll give you part of it. All right, you do the rest. It's a geometric series. Come on, what is x to the n? Good, that's it. This is it. This will not be given to you. But we will give you sine of x, cosine, inverse, tangent, e to the x. I think that's about it. That's the one you have to know. If you don't know that one, then you have to do this way, but that's such a pain, right? Differentiating that. Okay, on the other hand, even if you have this still doesn't look anything like that. In fact, the power is kind of off. We can adjust for the square here easily, but this thing squared is a problem. So let's first adjust for this x squared. That's the first thing we have to do. So that's the adjustment here. This will become negative x squared to the n, or minus 1 to the n, x to the 2n. Okay? So we have that. We still need to go that way. So how are these two things related? When you have a fraction here, what can you do so that the fraction would gain a power? Think of an operation that we do in calculus. What'd you say? Derivative, right. Now think about if you have 1 over x. When you take the derivative, you get negative x to the minus 2. So you gain the power here from 1 to a 2. Differentiating a quotient generally gains a power downstairs. That's the same thing here. So note the derivative of 1 over 1 plus x squared is equal to negative 2x, 1 plus x squared, right? So what do we want? We want that. So what we want, okay, is negative 1/2 of the derivative of that. And this part here, we have a Maclaurin series. Right there, right? Okay, so I'm going to use my existing Maclaurin series, differentiate that, multiply that by negative 1/2, and then that will give me what I want. So once again, we took advantage of this, modifying that to get that. Take derivative, multiply by negative 1/2. So we'll pick it up from this line. And let's write a few terms out of this, and then we can differentiate that. N equal to 0, we get 1, right? N is equal to 1. N is equal to 2. N is equal to 3. N is equal to 4. Now let's take the derivative. Notice my n equal to 0 term is gone because it's a constant. So my n is equal to 1 term is negative 2x. N is equal to 2 is 4x cubed minus 6x to the 5th plus 8x to the 7th minus 9x to the 8th, and so on. So that's n equal to 1, 2, 3, 4, 5. Oop, that's a 9, right? Wait a minute. No. 1, 3. 5, 7. That's 10, right? So, sorry. Minus 10x to the 9. Okay, because the next one is x to the 10th, negative x to the 10th. So that's where this guy comes from. Okay, now let's form the Maclaurin series for this. We're starting at 1, so we'll start at 1 to infinity. We have the alternating part. Let's do that first. So does that take care of the sign pattern I see? Or do I need to adjust the power by 1? Is this good? Yeah, so minus, plus, minus, plus. I want even ones to be positive, and we got that. Okay, let's take care of the 2. 2, 4, 6, 8, 10. That's just 2 times something. 2 times what? N, yeah, exactly. 2n. So 2 times 1, 2 times 2, 2 times 3, 2 times 4 gives me that. Okay, and then the powers of x. What do you think the power of x should be? 2n minus 1. So this will give me all the odd powers. I want the first one to be 1. When n is 1, we have 2 minus 1. Good. When n is 2, we have 4 minus 1, 3. Excellent. And it fits. Okay. Finally, remember we saw on the last page the Maclaurin series that we really, really wanted. Was this, right? So I have this part. So this is the derivative of that. So I got that. I got taken care of. Now I just need to bring the 2 minus 1/2 into here. Remember, anything doesn't have n attached to it can move in and out of the summation. This one doesn't have any summation. We'll bring it into here. So it's going to cancel out this 2. 1/2 times 2, they go away. We'll come back to the power of minus 1. All right, so if I bring in extra power of minus 1 into here, this would bump it up to n plus 1 for the power of minus 1. But notice the right answer actually has the exponent as n minus 1. It's the same thing, right? N plus 1 and n minus 1 have the same pattern of plus and minus, right? So these two are exactly the same thing. Yes? The starting index changed because we lost the constant. Right? N equal to 0 gave me a 1. When I differentiate it, it's gone. So my new series starts at 1. So let's write this out here. Here's a 0. And that's my n equal to 0. And we never count the extra zeros, right? We don't want to start at 0 just because the way series are. Okay, so here's the answer we wanted. So normally you would get this one following the method, but to match up to the answer, we had to adjust that to n minus 1 because it doesn't change the pattern. Okay, questions on this? No? Good. Okay, next one, let's look at number 12. This one is not as interesting, but oh well. We want to find the length of the curve given by y is equal to x cubed over 3 plus 1 over 4x. And x goes from 1 to 2. All right, so who remembers the formula, one of the formulas for length of a curve? Yeah, what do you think?
The integral of the square root of 1 plus dy dx squared.
Good. dx, right? All right, so that's the one way to do it. We could also do dx dy and then integrate over y. Okay, there are two ways to get an arc length. And for us here, the first form is much better. We're given a range being x. We're given a function y as a function of x. So the first one is better than the second one. We'll use this one. So first we need dy dx. So that's going to be x squared minus 1 over 4x squared. Then let's form the 1 plus that. Let's square that first. So we get x to the 4th minus twice of these two multiplied together. So 2 over 4, right, minus the last thing plus the last thing squared. And that gives me this part. Now let's add 1 to it. So we get x to the 4th. 1 minus 1/2 is plus 1/2 plus 1 over 16 over x to the 4th. Okay, eventually we have to take a radical of that. And if you take the radical right now, it doesn't take you anywhere useful. So let's do something to this. Let's combine it. Put them all over 16 to the 4th. So the next one, the first one becomes 16x to the 8th. The next one is multiply this by 8x to the 4th. So 8x to the 4th. The last one is a 1. Next, again, remember we're going to take a radical. So we're going to try to put these things as something squared so we can take a radical. And the top one turns out to be 4x to the 4th, the quantity squared. Right? So 4x to the 4th squared is 16x to the 8th, plus twice of these two multiplied together, plus the last one squared. So that's what we get. And now we can take the radical of that pretty easily. 4x to the fourth plus 1 over 4x squared, right? And that simplifies again. 4x to the fourth over 4x squared is x squared plus 1 over 4x to the minus 2. We're going to integrate next, so I'll write it that way. All right, now we integrate. Arc length is x range from 1 to 2, 1 to 2, and then the stuff we integrate is what we just did, and that's equal to x squared plus 1 over 4 x to the minus 2 dx. So 1 over 3 x cubed minus 1 over minus 1 over 4, right. X to the minus 1, 1 to 2. So 8 over 3 minus 1 over 8 minus 1 over 3 minus 1 over 4 Okay, this eventually turns into 59 over 24. Okay? Question? No? Okay. Now, if you forgot the formula for arc length, remember we estimated that by taking a straight line segment like that. Right, this was dx, this was dy. So this is roughly equal to radical dx squared, delta x squared plus delta y squared. And if you divide everything by, if you factor out delta x squared, then you get what kind of looks like what we want. Right? And then by taking the limit, letting the dx, delta x and delta y shrink to almost 0, these become the normal dy dx and the dx. So once again, if you forget that formula, just remember where it came from. Just a straight line segment, and then shrink the change in x. Okay, next one is number 10. We have to integrate this. Okay, so we've been through a lot of integration here. In this course, we have trig substitution. You don't see a radical here, so that's probably not a good candidate for trig substitution. Normal integration by substitution is not going to do it. Integration by parts looks pretty complicated, not a good idea. So the other method we got is to try a partial fraction expansion. And hopefully we end up with simpler stuff to integrate. Question? 4 on the top. You're right. That's a dx here. Dx. Does that look like dx? Close enough? Close enough. Okay, so we got to do a partial fraction here. Let's do 4 over x, x squared plus 4 equal to, we look at the denominator. The first one is a distinct linear, so just a over x. The second one is an irreducible quadratic. And what do you put on the top for irreducible quadratic? Right, a linear term. So this is an irreducible, how you spell it? What? Not factorable. Quadratic. So we put a linear, right? Remember, you always put something on the top that's 1 degree lower. Here you have a linear, you put a 0 degree, a constant. Okay, let's multiply this to the right-hand side. Therefore, we get a 4 times a times x squared plus 4 plus bx plus c times x. Right? Let's multiply stuff out. Ax squared plus 4a plus bx squared plus cx. Let's rearrange things a little bit. A plus b x squared plus cx plus 4a. Left-hand side, only a 4, so it's 0x squared plus 0x plus 4. And for these two to be equal, we have to, everything has to line up. So a plus b must be equal to 0. C must be 0. Well, that's good. And then 4a must be 4. So this is a simple one here. Right away we see c is 0. Right away we see a is 1. So a plus b being 0 means b has to be negative 1. So now we see this. A over x. So a over x plus bx plus c over x squared plus 4. So here's bx, sorry. C is not there anymore, so we don't have an extra constant here. Okay, now we integrate. 1 to 2. First one's easy. The second one is also pretty easy. Second one, you can do that by a substitution. Let u be x squared plus 4, and du is 2x dx. All right? Okay, after you do that, this becomes pretty simple. So we're out of time here. I'll finish the rest of this before I upload the notes. Okay, I'll complete this, and you'll see the completed rest of the steps. All right, so we'll continue this on Wednesday and Friday. If you have not participated in the survey and you didn't like the questions we went over, that's your own fault. You didn't vote. If you want to influence that, go vote. See you Wednesday.